So I'm going to talk about something that's related to one of my interests, which is in one of my units in computing. But actually, it's probably of more interest to physicists than computing people. And it's actually also related to bioinformatics. One of the things I do mention in the unit is that one of the areas of research in advanced computing is actually storing data in DNA. And being able to now encode and decode DNA much more efficiently has really made that take off a fair bit. It's a wonderful storage mechanism, but people are still a bit spooked out by it. What I want to talk about today, though, is quantum computing. You've probably all heard that quote. If you think you understand quantum physics, you don't understand quantum physics. And originally attributed to Feynman, I think, but that's a bit dubious. I'm sure there's people here in this room that actually... Is there anyone here who understands quantum physics? No? Okay. Well, if you do, then there's some... So, we're all used to dealing with normal computing. Physics people are good at computing because they have to be. Everything's done by computer these days. So you know how normal computers work. The von Neumann architecture is fairly straightforward. It uses bits, zeros and ones, that's fine. A quantum computer is a bit different. If you know a bit about quantum physics, you know that essentially it's looking at the spin of particles. That spin can be interpreted as 0 or 1, but more importantly at the quantum level there is a degree of uncertainty. So quantum computers use what are called qubits, quantum bits. A qubit is also technically either 0 or 1 eventually. So you can use it just like a normal bit, but it's a bit plus another set. Until you actually open the box and observe things, a qubit exists in superposition. And you'll know that that also happens with quantum states. So the point is that with a computer, you may not know what the value is, but the bit is either 0 or 1. It's one or the other. It can't be somewhere in the middle, it's either 0 or 1. A qubit officially is both 0 or 1. And you could say every value in between, but really we're looking at the 0 and 1 at the same time, until such time as we observe it. And that's where the difference starts. With a bit in a computer, if we open it up and had a look at the computer, we'd find out what the value of the bit is, even if we can't otherwise check. If we don't know the value of a bit, so we've randomized it and haven't looked at it yet, we're just ignorant. It has a value, we don't know what it is yet. With a qubit, it literally does not have a value until we open up the box and have a look at it. Or if you want to look at it, it does have a value and that value is both 0 or 1. So that's the fundamental difference between a qubit and a bit. And that fundamental difference, plus a few other things, allow you to do a few really funky things. Now, as you probably noticed, I'm not a physicist, right? So I'm not going to give you any advice on the physics of quantum computing. Talk to an expert. You have some quantum physics experts. What I'm trying to do is talk about how this applies to computing. If I get some part of physics grossly wrong, please let me know, but in general, I will do the best I can. The important things are that qubit value, the superposition, and then also entanglement. Because once two qubits are in superposition, you can entangle them. You can make it so that their states are related to each other. That has all sorts of really useful properties. So for example, if you move those particles apart, if the particles are entangled, what you do to one affects the other. Now, again, I don't know the physics of it, but I've read some reports that suggest that that one affecting the other may not be bound by some of the normal laws, such as, say, the speed of light. But that doesn't apply to quantum computing at this point, although it does make life fairly interesting when you talk about quantum communication, which I'll talk about later. The important thing, though, is that when you have two bits, you can flip one of them into one value, the other one into the other value, and you have 4 possibilities, right? But you have to do that manually. With qubits, you can set them up so that they are entangled. And when we get to the observation, you have multiple choices to how to observe a qubit. That multiple choices makes the entanglement, the possible values you can get, quite a lot richer than normal. I haven't included it here because there's not enough time, but there's a really good web cartoon called PhD, or PhD Comics. They've done a YouTube video on the basics of quantum computing, which is mostly accurate and highly entertaining, so I can recommend that. The point is that the superposition ends up being not just a superposition of two separate qubits. Effectively now we're looking at a superposition of all possibilities of all of the qubits that are entangled, which is very, very useful. The next bit is observation. As I said, with a computer, if we could look inside the computer, and we can if we need to, we can find out what the value of the bit is. With a quantum computer, life is a bit different. We have two different ways that we can measure what the value of that bit is. More importantly, as soon as we choose one of those two methods to investigate what is the value of this bit, the superposition collapses and the qubit will be at one value or the other. And after we've measured it once, it stays at that particular value. In fact, all the entangled qubits also tend to collapse depending on exactly how you do it. And the really cool thing is the way we choose to measure it affects the outcome of the measurement. Just again, like measuring the spin of quantum particles. So that gives us two things. One, we have more choice. We get more interesting results because we have two different ways of observing something, which impacts the experiment. But also because we now know if somebody has observed something. Why would that matter? Well, think about cybersecurity. What impact is it if you know whether somebody has observed some part of what you're doing, some part of your system, say your communication? So that's one thing that people are looking into with some interest. I'm not going to go into a huge amount of detail, partially because I have looked at a huge amount of detail and don't understand half of it. But what I can tell you is that the state of the art in quantum computing is advancing at a huge pace. A few years ago, there was one manufacturer of commercial quantum systems, which is D-Wave. Wikipedia, when I looked up the list a couple of days ago, had more than 100 companies or special centers that were specifically working on quantum computing. Quantum computing is really taking off. These companies are getting big enough that they are acquiring each other, merging, spawning new spin-offs, etc., etc. Quantum computing is becoming a commercial enterprise. The biggest quantum computer isn't very big. It's 65 qubits, that's IBM one, and they crowed about that a lot recently. There's a bigger one coming out hopefully later this year. On the other hand, D-Wave is selling a 5,000 qubit system, but it's not a general quantum computer. The IBM one is a general computer. You can use those 65 bits for general computing. The D-Wave one, all it does is what's called quantum annealing. All it can do is optimization. But it can do that really, really well. There's certain types of optimization that you can do with that D-Wave computer, which are much, much faster than if you were using a standard system. What sort of things can you optimize? Well, think of the design of any sort of car or plane or whatever. You want to optimize, say, the airflow. There are companies like Boeing and Lockheed who have access to these D-Wave quantum computers who are actively using them in their design phase. Why? Because you can do something in minutes or hours with one of those that would take days or years with a modern supercomputer. So that even though it's not a full computer, it is revolutionizing what can be done. Even about 6-7 years ago, some companies like Google were spending millions and millions of dollars, well, in fact probably hundreds of millions, on getting some of these systems to work on them. And they just weren't accessible to us, to everyone else. That is also changing. The biggest problem with the state of the art, the biggest problem with building a quantum computer is something called decoherence. Because once you've observed the quantum particle, once you've observed the outcome, then you have information, that state collapses. That means that you have to be able to contain the quantum particles in such a way that no information can leak out that could potentially be measured. But as soon as some information leaks out, the whole state collapses and you've lost that bit. And that's the big problem. And there's a lot of research, including in Australia, on how to do that. At the moment, it's all very cold, very specific elements, but there's a lot of work being done on doing it with different hardware, which again I won't go into detail, but it makes interesting reading. The big change recently has been quantum clouds. If you want to go and learn how to program a quantum computer, if you want to actually interact with a quantum computer in real life, you can for free. So IBM, for example, has released Qiskit, and you can use that development platform to do some programming, and you can have a certain amount of time with either a real quantum computer or more likely a simulated one, which frankly is probably good enough as long as you're not trying to break any world records. Amazon has a service they call Bracket. Microsoft has Azure Quantum, and there's another service called Quantum Inspire, which reaches out to a whole bunch of different services like D-Wave and allows you to use their machines. Microsoft also has Q#, which is like C# but for quantum computing. You can download that today and start playing with programming quantum computing. It's simulated on your desktop, but it is quantum computing. Now, that's all great. I'll talk in a moment about what it can do, but let's have a look at just what IBM wants to do. IBM has set up a division on this. They are focusing very much on quantum development, and they're looking at growing their roadmap. At the moment, they've got a 65-bit one. For this year, 2021, they want to release a 127 qubit one. No word yet whether they'll manage. But they are saying that in 5 years' time, we expect to have usable generic quantum computers. By 2030, we expect people to be able to go on the cloud and choose to use quantum computing resources, just like these days we can spin up Amazon instances and use normal computing resources. Okay, so what's the impact of all this? Well, quantum computing can do a few things differently from the way normal computers do things. Normal computers have certain restrictions. Quantum computers have different restrictions. My unit TFCS talks about how the systems work and what can and can't be done. So there's a whole area on how difficult it is to solve a particular problem called complexity theory. And if you've done a unit like DSA, you've touched on it. DAA takes you a bit further into it. But the point is, there are some problems that are really, really hard to do. Think of the traveling salesman problem or something like that. Quantum computing allows you to do some of those things much more easily. Not all of them, but some of them. A popular example, for example, is the main form of I've forgotten the word now. When you're trying to encrypt your credit card details or whatever, when you're using HTTPS, that encryption is basically done in a large part by factoring large prime numbers. Guess what? With quantum computing, there already exists an algorithm that allows you to do that in polynomial time rather than exponential time. So if you have general access to quantum computing resources, your 256-bit encryption just isn't good enough anymore. Your 512 is probably not good enough, and in fact, no matter how fast you grow, in a few years that just will not be sufficient anymore. There is quiet word that some years ago, American companies were warned to move to a quantum-safe encryption algorithm, and many have done so, but all of that is very unofficial. The point is that computing is changing, everything we're doing is changing, and we have to make sure that we keep up with it, because quantum computing is going to give us a whole new look on how to do things. One of the big things that has been in the media recently is quantum supremacy. What is quantum supremacy? The main definition is, can we do something with a quantum computer that we can't do full stop with a normal computer? Google claimed to have done this last year, but it's sort of a bit iffy. But their claims certainly hold some water. D-Wave have claimed a similar thing for quantum annealing rather than general. Google has recently created what's called a time crystal, which is another state of matter using quantum computing. Again, it's a bit more detailed. There's a preprint available, hasn't actually gone through peer review yet, but if you look up Google time crystal, it'll give you a bit more detail. I've run out of time to talk about that. The really big one I want to talk about though is quantum communication. In 2016, China launched a satellite for quantum communication, which communicates between two base stations, and all it does is exchange keys for cryptographic transfer. So you can actually get a key from the other station. Why are we using quantum communication? Because if somebody intercepts what you're doing, the whole thing collapses. You can see that someone has intercepted it. Not to mention the fact that you've got linked particles, life becomes a bit interesting. Quantum communication is popularly considered unhackable at this point, which is a nice advantage to have in your communications deal. That's been researched around the world anyway. I haven't had the time to go into much detail with fairly much anything, but I do want to say quantum computing is going to revolutionize computing in your lifetimes, probably in the next 10, 20 years. And people are going to be looking very urgently for people who know how to program quantum systems, because no one's teaching that at the moment, so we're not turning out graduates who can do that. If you want to pick up a hobby and you know a bit about quantum mechanics, I can consider that maybe a worthwhile thing to have a look at. So thank you. I'm happy to take questions.